So today we're going to be looking at problem 20 and 22 in chapter 7. And what question 20 asks is use the Rydberg equation to calculate the wavelength in angstroms. This is a key point in the problem of the photon absorbed when a hydrogen atom undergoes a transition from n equals 1 to n equals 3. So those are just energy levels. It's going from energy level 1 to energy level 3. So as I always state, write what you know down first. So your known is your first energy level, your initial energy level is going to be 1, and final be 3. Okay, so I'm going to just kind of give you a visualization of what you're actually looking for and what's actually happening in this problem. So I'm going to just draw out a little bit of it, like an energy level type diagram. And initial equals 1, and final equals 3. And what kind of happens is you have a photon coming down, say from a light wave or from whatever EM radiation is going on. And what happens is the energy goes to an electron in the hydrogen atom. So it's going to have enough energy to essentially jump up to the third energy level. So it's going to get here. And so what this problem is asking you is to find the wavelength of this photon going into the atom and exciting the electron to jump to the third energy level. So this problem is really straightforward. They tell you to use Rydberg's equation. So we're going to write that out, which is 1 over lambda, which is your wavelength, which equals your Rydberg's constant, which is something you should memorize. Multiplied by the inverse of n initial squared minus n final squared. And these are essentially your principal quantum numbers. I like to visualize them as energy levels. It's a lot easier for me to see them when I do the problem as that. So it helps you, really helps me out. Okay, so now what we want to do is we want to find essentially the wavelength, right? So what we have to do is essentially flip this equation around so we can have the wavelength on top. So all we're going to do mathematically is flip this over and then flip this over. So now we have essentially your lambda, your wavelength on top, divided by 1 over r multiplied by 1 over n initial squared, multiplied by 1 over n initial squared minus 1 over n final squared. And so this is the setup you should have to find the wavelength. So now all it is, you just plug in what you have, the constant that you were given. So your Rydberg's equation, your Rydberg's constant is 1.09677 6 multiplied by 10 to the 7th inverse meters. Let me extend this line out because it's going to be kind of a long number. Okay. Multiplied by 1 over 1 squared minus 1 over 3 squared. So then this eventually just equals 9. This eventually equals 1. So once you do this part out, once you calculate this part, it should equal 1.0257 multiplied by 10 to the negative 7th meters. And that makes sense because your inverse meters will eventually flip to the top. So just to always make sure that logically these units always they always correspond. So this wavelength is in meters. But remember when I said in the beginning, the main point of this problem is to find the wavelength in angstroms. So all we do is do a quick conversion of this. So just write out what do you have in meters again? So now just remember that 1 meter is really 10 to the 10th angstroms. Right? Just remember that conversion. So then now you have 1,025 angstroms as your answer. So this is really what the wavelength is in angstroms, and this makes sense because you're essentially using a photon. Well, a photon is extremely small, and this photon has enough energy to just move the electron. So make sure also that your problem makes logical sense. And now we're going to move on to the second problem we're going to talk about today, which is problem 22. I'm just going to draw a dividing line because I kind of want to show you at the end the difference between equations. So now problem 22 is asking you to calculate the energy difference for this transition for 1 mole of hydrogen atoms. And the 1 mole of hydrogen atoms is really important. So just remember that when you're calculating this problem. So we're going to write down Rydberg's equation again, but we're going to do it for energy. So the Rydberg's equation for energy is delta E, which is your energy difference, equals negative R, it's kind of messy R here, multiplied by 1 over NF squared minus 1 over NI squared. Okay, so now you're kind of left with this idea that you have a Rydberg's constant given in the first problem, but you really want to find this in energy, right? Because let's kind of do a unit analysis really quickly about what you want at the end. So energy is always given in joules, right? So you kind of want a joules unit at the end. But the and you know that these two are just integers. They don't really have units. So you're going to have some blank unit here. So I'm just not going to write anything here. It's going to be completely blank. But then that leaves that means that you have to have some type of unit here that's going to be joules, right? But the problem is that for your constant here, you only have it in inverse meters. So you have to convert this one to joules. And the way that you do it, I'm pretty sure they give it to you in the book, but the real reason you get to this constant for energy is you really take your constant here, which is 1.096776 multiplied by 10 to the 7th inverse meters, multiplied by Planck's constant, multiplied by the speed of light. And I didn't have room to write it completely, so I'll write a little bit more underneath here. So this is 6.626 multiplied by 10 to the negative 34 joules per second, multiplied by 3.0 multiplied by 10 to the 8th meters per second. And actually probably want to write this actually down here now. So let me just kind of write this down so you can see all the units in play here. And I'll replace this with your R here. So essentially it's your Rydberg's constant you're given here multiplied by the Planck's constant multiplied by the speed of light. So now we're going to look at unit analysis to make sure that we're getting joules at the end. So we know that meters will cancel out with inverse meters, and that seconds will cancel out with inverse seconds. So now we're left with joules, which is exactly what we want for our constant. So now our constant will be 2.18 multiplied by 10 to negative 18 joules per photon. And the photon is actually implied per photon. The photon part is implied. We don't really have in our unit analysis here, but this is for 1 photon. You always have this amount of joules for your Rydberg's constant. So now what we can do is just a simple plug and chug into this equation. So now we have your delta E equals negative 2.18 multiplied by 10 to the negative 18 joules per photon. So I'll put joules here. Multiplied by, I'll move out of the way, 1 over 3 squared. Kind of messy here, I erase that. 1 over 3 squared minus 1 over 1 squared. Okay, so now what we have here is we have, well, let me just simplify this part down. Hold on. So you have essentially 1/9 minus 1. So if you keep on simplifying it down, you'll realize that you'll get essentially negative 8/9. And these negatives will cancel out, so you can erase these negatives here. You get a positive answer. And so when you do this, you're going to get 1.93778 multiplied by 10 to the negative 18 joules per photon. And this makes complete sense because when you look at a positive energy difference means that you're adding energy to it, right? So if this is positive, it means that I'm adding energy to this hydrogen atom, which makes complete sense. So make sure you always use your logic and think all the answers out when you get them, because then if you do that, you're definitely you'll definitely get the right answer. So if it's negative, that means that it's losing energy. If it's positive, that means that it's gaining energy. And because it's transitioning to a higher energy state, then you know that it is gaining energy to get to the higher energy state. So now the trick is to get it into moles. And this is just a really simple Avogadro's number equation. Conversion. So you're going to do essentially 1.93778 multiplied by 10 to negative 18 joules per photon, multiplied by 6.022 multiplied by 10 to the 23rd, kind of getting small here, photons, is that right? Yeah, photons, ooh, kind of small there, but that's just photons per 1 mole, right? So now you cancel it out. So now you have the right units you need it, which is joules per 1 mole. So just now it's a quick conversion at this point, a quick calculation at this point, where you get approximately 1.17 multiplied by 10 to the 6 joules per mole. And that's your answer for 22. So the reason I did these two problems was because I wanted you to see the difference between using your wavelength equation and your energy equation. And sometimes these equations seem kind of abstract, but just remember that when you're looking for a wavelength, you want to use the wavelength equation and the Rydberg's constant that involves inverse meters because you're looking for a wavelength. But if you're looking for something, say an energy, you want to use your energy equation with the Rydberg's constant that involves energy. And I'm pretty sure that this is in your textbook. If not, you can look it up online. But this is how you get to that number if you ever forget. So, good luck.